Okay, so 7.8 is called variation. And so we're going to be looking at some specific styles of equations that show a relationship between two different amounts. That's what a variation equation does. It shows how one quantity changes in relationship to another. And so there's a couple different types of variation problems that you will encounter, and I tried to break it up by the type. I tried to give you the general example, and then I tried to give you some specific examples as well. So the first type of variation we have is a direct variation, and that involves two different variables that increase or decrease together at the same time. And so the very general format is going to be y equals k times x. And anytime you see this k in any of the equations today, this k is called the constant of proportionality. And so that's going to change depending on what your problem is asking for. And a lot of times your problems will be set up to where you have to figure out what that k is before you can actually apply this information. So direct variations, that's where two things increase at the same time or they decrease at the same time. And so the first type of example that we have of this, you don't have to do anything with. I'm just showing you that distance equals rate times time. We could consider this a direct variation problem because as the time increases, so does the distance. So the amount of time you're traveling determines how far you're going, theoretically, if your rate stays exactly the same. That is a direct variation. If you don't go for very long, then your distance isn't going to be very long, and things like that. So there's nothing to do on that problem. That's just showing you a generalized example of how distance versus the time can be a direct variation. The other problem, the B, is actually more like what you're going to see on some of your homework, and it's going to walk us step by step through how this works. So this is talking about a drug. These are going to be a lot more real life applicable than some of the other problems maybe that we've had. It says the amount A of a drug, theophylline, is given to patients directly proportional to the patient's mass, which is M, in kilograms. So the amount of the drug is A, and the mass of the patient is M. The first thing we have to do is we write a variation equation. You're going to use this really general format to write the variation equation. So here's how it's going to look. The amount of the drug that we give is dependent upon the rate of proportionality times the mass of the person. We don't know what that rate is yet. This is just a very generalized example, a very generalized equation, because at this point we've got three different things we don't know, and that's not very helpful. But the amount of the drug that we give to somebody is going to be proportionally determined by the weight of that person. So maybe you give like 0.2 grams or milligrams or whatever of the medicine per, kilogram of mass or something like that. We don't know what that is yet, and that's what we're going to have to figure out. So usually these problems work out where either they will give you the very first part, they will give you the equation, or you have to come up with it. And the way you come up with it is you use the variables that they give you instead of the y equals k times x, and you write it down like this. You will still have the k in there. Step 2 is usually where they will give you everything besides the k, and you will solve for the k. That way you can figure out what is that proportionality rate that we need to have. So 2 says if 150 milligrams is given to a boy whose mass is 30 kilograms, determine the constant of proportionality. So the 150 milligrams, that is the amount of the drug. This is our A. And the 30 kilograms, that's the mass. So the only part we're missing is the K, so we're going to plug those amounts in and solve. We would have 150 equals K times 30. So if we're trying to solve for K, we would divide both sides by 30. And we find that we have K equal to 5. For every kilogram, we're going to give 1 milligram of medicine. No, 5 kilograms of medicine, excuse me. Erase, start over. Every kilogram for the mass, we're going to give 5 milligrams of the medicine, is what we just determined. So that means we can actually have a nicer equation than A equals K times N, because now that we know what K is, we know that actually it's a equals 5 times m. That doesn't mean we're going to go back and change our first answer at all, because the first one is right. We didn't know what k was. It was very generalized. Now we know what k is for this case. It's going to be 5. So the next question will always utilize what we just learned. How much of the drug, that's our A, should be given to a patient whose mass is 62 kilograms? So we're asking for the A, we're given the mass. With our new and improved equation, the fact that we know what the mass is means we can figure out how much of the medicine we need to give. Because A equals 5 times 62. A equals 310 micrograms or milligrams of the theophylline. So something that's a little bit different from these problems than a lot of the other problems we've had. One, we haven't had a ton of word problem things in this class. Two, they're going to work you step by step through so that you start off with a really generic equation, then you earn or learn the rate of proportionality, and then you're going to use that to answer an additional equation or at the end, where either they're going to tell you how much of the drug or they're going to tell you the mass of the child, and then you're able to figure it out because of what you've done already. So you're going to work step by step through. You're going to use the pieces you just acquired. Are there questions on that one? Told you, they're a different flavor from the rest of Chapter 7. But we're going to work through lots of examples so that we kind of get used to that flavor and learn how to answer the questions the way that they want us to. All right, let's do one that's not necessarily like real world applicable. This one says y varies directly as the square of x. So right there, I'm going to pause. It says y varies directly as the square of x. Our very general equation up top is y varies directly in terms of just x. So if I know that y varies directly in terms of the square of x, that's going to look like y equals kx squared, like this. So your equation can change a little bit depending on what it says. If it doesn't say the square of x or the cube of x or x divided by 2, then you're going to assume it's just a regular old y equals k of x, like we did up there with a equals k of m. But this one changed it a little bit, and it says y varies directly as the square of x. Then it's going to give us some more information. It says if y is 15 when x is 5, determine y when x is 10. So this problem is still doing all 3 steps of the previous problem. It's just all done at once. Because really what we just did right here was step 1 of the previous problem. Step 2, it says y is 15 when x is 5. So if I put y is 15 and x is 5 in here, notice the only thing I didn't get to know was the rate of proportionality. That was step 2, where I have to find that rate. And then step 3, we use that rate to help us determine what y is. So we're still doing all 3 steps. It's just worded differently, and it didn't break it down as much as you had in the previous problem. So for here, for y is 15 when x is 5, I have to plug these values in. Y is 15, I don't know what k is, and then my x they're telling me is 5. That doesn't mean x squared is 5, it means the x is 5 and I put it in, and then I'm going to square it. So that means 15 equals 25k. Divide by 25, and I get 3/5 equals k. Proportions can be fractional. Proportions can be whole numbers. You will not, let me double check all the problems before I say will not. At least for k's, I don't think your k's are ever decimals. They always want it as a fraction, just simplified. So the reason why we have to find this rate of proportionality is because the very last section of this sentence says determine what the y is when the x is 10. If I don't know what k is, it doesn't matter if I know what x is, because I have to know at least 2 of the 3 of my variables in order to actually solve. So So you will always have to figure out what your rate of proportionality is here before you can figure out your final answer. Because I'm still going to use the y equals kx squared, only I don't know what y is. I just found out my k is 3/5 and my x is 10. So y is 3/5 times 100. I'm going to stick that as 100 over 1. Sorry, I went off screen a little bit. Simply because I'm going to do some simplifying on the front end. I know 100 is 5 times 20, which means there's a 5 up here and a 5 down there. So I find y is 3 times 20, which is 60. Again, you don't have to simplify on the front end. You could have taken 3 times 100, which is 300. 300 over 5 would still give you 60 in the end. It still works. So these are very direct variations. And we see that because when we had x is 5, our y was 15. When x was 10, our y is 60. They both went up at the same rate. And that rate was 3/5 here. Above, they both went up at the same rate as well. Are there questions on direct variation problems? How we found them, how we use the very general format of y equals k times x, how that changes if it tells us it changes where it says the square of x. We changed it to the square of x then in our equation, or how we find that rate of proportionality or any of it. Because even as we go through the different types of variations, a lot of the steps that we're taking, a lot of these processes are going to be the same. All right, let's flip over. If there is direct variation, logically, there is inverse, or indirect is kind of what I was going to say, but inverse variation. Inverse variation involves two variables in which one variable increases as the other decreases. They're going to do the opposite of each other. So you can see this written out in two different ways. You can see it as y equals the rate of proportionality over the x, or you can see it as x times y equals that rate of proportionality. Either one works. Either one is great. I think I usually stick with the fractional form, because they're going to have you find that y a lot of times anyways. And so, again, the very first example that I use is the distance example. And I just use the distance example as a example of direct variation, because I told you that the time and the distance are increasing at the same rate. But if you reorder your distance equation, and we think about it in terms of time equals distance divided by rate, that's where we get our indirect variation. As our rate increases, our time decreases. The faster you go, the faster you're going to get your trip done. So if I'm going 30 miles an hour, it's going to take me a lot longer to get there than if I'm doing 60. So the amount of time is indirectly related to my rate. They're opposite. And so sometimes the same type of equation can be looked at from two different perspectives that give you different variations depending on what it is you're focusing on. In the first one, we focused on the distance and the time. Here, we're focused on the rate and the time. That's why we can say that this is an indirect variation. So let's look at an example. It says the amount of time, little t, it takes for a block of ice to melt in water is inversely proportional to the temperature of the water, which is a big T. That means the warmer the water, the faster it's going to take to melt, and vice versa. If you have really cold water, it's going to take that ice forever to melt. So that's what it's telling you. So we need to write the variation equation. This is where we're going to use that really general equation right up here with the variables that they're going to give us. So it says the amount of time t, that's little t, equals, we have our rate of proportionality that we don't know, divided by the temperature of the water. That will tell us how fast this ice will melt. The higher the water, the less amount of time. The colder the water, the more amount of time. They're inversely related. As you up one, the other one goes down. It says, if the block of ice takes 15 minutes to melt in 60-degree Fahrenheit water, determine the constant of proportionality. So again, they're going to give us all the pieces we need. They give us the little t, they give us the capital T, we figure out what K is. It says 15 equals K over 60. So you're going to take 15 times 60 to figure out what K is. 900. The constant of proportionality is 900 in this case. So that means a more accurate representation of the equation would be T equals 900 divided by the temperature of the water, and that's going to tell us how long it takes for that ice to melt, which is what we use for the next step. How long will it take the ice to melt in 50-degree water? Well, the time is the little t, that's what we don't know. So we're going to take 900 divided by 50. And we're going to find out that little t is 18 minutes. We use the general equation to write a more specific equation for our specific problem. Then they will give us the information without the constant of proportionality, so we can figure out what that constant of proportionality is for this specific problem, because that obviously changes from problem to problem. And then the last one, they will either give you one of the two missing pieces so that you can figure out the final solution for that. Questions on that one? All right, let's do another example. All right, good. I can fit it on there. This is a lighting example. It says the illuminance, or capital I, of a light source varies inversely as the square of the distance d from the source. So again, this one's following suit kind of like our last set of examples, where we're still going to use the general formula up here, but this time it tells us that the illuminance, the I, is going to vary directly, or inversely to the distance squared. So instead of y equals k over x, I'm now going to have, am I down there? Okay. I equals k over d squared. Still using the general inverse variation formula, but I have to tweak it because it says the square of the distance. Just like I had to tweak it on the last problem of the direct variation. It says, assuming that the illuminance is 75 units at a distance of 4 meters, determine the formula that expresses the relationship between the illuminance and the distance. So this one takes us basically through the first two steps that we usually do with these problems, and then we get to stop. Because it wants this. It wants the more specific formula that we come up with after we find our K. We've already done part 1 just by writing this. So now they give us a specific example where we have 75 units for 4 meters. So we have 75 units equals K over 4 squared. This will allow us to find the K and write the more specific formula that they want to express the relationship between the illuminance and the distance for this problem. So this is 75 equals K over 16. So I'm going to take 75 times 16 to figure out my K. 75 times 16 is 1,200. So they don't ask me to figure out, okay, what is the distance if the illuminance is this, or what is the illuminance if the distance is this? They simply say, determine the formula that expresses the relationship. I have the illuminance equals 1,200 divided by the distance squared. Now, no matter what they want to find out, they have the given formula that will help them to determine either the illuminance of the lighting or the distance in relation to that lighting for the specific lighting source. So sometimes you're going to take it all the way through and you're going to answer an additional question. Sometimes they just want you to get a more accurate formula and leave it at that. Questions, clarifications, comments? One thing I would say is when it comes to making your note card, I would look at the practice test. If you have the inverse and inverse and direct variation problems, I would write down the general formulas for them. That's a good thing to put on there. That way you can remember, oh yeah, I've got to change those. I've got to find those rates of proportionality. All right, let's flip over. We've got two more types of variation. Yep, two more types of variation. Joint variation involves a variable that varies directly as the product of two or more other variables. So this one is direct variation, but you have more than one variable at play. So instead of just y equals k times x, I now have y equals k times x times z. I've got more stuff involved. And so the example we're going to look at is the area of a triangle. The area of a triangle is a very good example of joint variation. I don't know if you remember, and it's kind of going to give it away a little bit here if I state it first, but I'm going to state it first. The area of a triangle is 1/2 base times height. Now, we're going to determine that here in just a minute, so sorry, spoiler alert. But this 1/2 ends up being our k. The base and the height are the other two variables that are at play that dictate what happens to the area of this triangle. And so what happens is the bigger the base or the taller the triangle, the bigger our area is. So they both go up, they all go up at the exact same rate is what ends up happening, which is why we call it a direct variation. Or in this case, it's a joint variation because we have to take into consideration both the base and the height. So it says the area of a triangle varies jointly as its base and its height. So right there, I could write A equals KBH. If I'm trying to keep my general format for a joint variation problem, yes, I know I already told you what the K is, but we're going to see it actually does mathematically come out. But we did change our variables from X and Z to base and height, and we had the area. It says the area, if the area of the triangle is 48 square inches, when its base is 12 and its height is 8, determine the area of a triangle whose base is 15 and whose height is 40. So we use all of that first information to help us figure out what our K is going to be. And I'm going to show you that it does actually work out. Because we'll have 48 equals 12 times 8 is 96. To get K by itself, we have to divide by 96. And that actually is 1/2. I know I kind of ruined that for you because I already told you what it was going to be. So that means the area of our triangle is 1/2 our base times our height. And so that says determine the area of the triangle whose base is 15 inches and whose height is 40. One half times 40 is 20, so 15 times 20 is really what I'm doing, so area is 300. It says inches, so I'm going to put inches squared. As our base and our height went up, so did our area. So joint variation is just kind of a more specialized version of direct variation. It's just instead of looking at one variable, we didn't get to just look at the height or just the base. We had to look at both the height and the base of our triangle to determine the area. So I took the 1/2 times the 40, just because I do that in my head. So that gave me the 20, and then the 15 was just part of the problem. If I can do it without a calculator, I'm probably going to try. I didn't want to take 7.5 times 40. So, other questions?
Why don't you do 15 times 1/2?
You can, but then, like I said, I'd be taking 7.5 times 40, and in my head, I can't do that. 7.5 times 40 is still going to give you 300. It still works out the same way. All I did was I took 1/2 times this, because they're all being multiplied together. I can reorder this any way I want. I could say 15 times 1/2 times 40. This part I can do in my head. This gives me 20, so then I have 15 times 20, which gives me the 300. I just can't do 7.5 times 40 in my head. But it gives you the same answer. You're going to be using a calculator, so you type in 1/2 times 15 times 40, you're going to get 300. Other questions? All right, let's look at our last style of variation problems, known as a combined variation problem. Combined variation involves direct and indirect variation among 3 or more variables at the same time. So it's like, let's take direct variation, let's take indirect, and let's shove it all together, and we're going to figure it all out at once. So this one's straight out of your book, out of, I think, 467 is what I have written in my handwritten notes. I copied it down. This is going to look at a lot of different stuff at once, and so we're going to make some notes, and then we're going to come up with some equations and figure out how this is all going to work out. It says the owners of Perky Buns Bakery and Coffee Shop find that their weekly sales of their cupcakes, S, vary directly at their advertising budget, A, and inversely as their cupcake price, P. That's a whole lot of information, so I'm going to make a couple of notes. I like making notes with word problems. It says in there that the cupcake sales, S, varies directly with their advertising. So that means if they have more advertising, they sell more cupcakes. If they don't have very much advertising, they don't sell very many cupcakes. That's what it says. But then it goes on to say that their sale of cupcakes is inversely related to the price of their cupcake, which kind of makes sense. I mean, if you think about going to a cupcake store, if the price is outrageous, you're probably not going to buy that many. Like, you got to find that sweet spot of where people are willing to buy a cupcake at a certain price. So these vary inversely. So then I'm going to look at what else they tell me. It says when their advertising budget is $400, so I'm just making some more notes. Advertising budget is $400, and the price of the cupcake is $1. They sell 6,200 cupcakes. That's a lot of cupcakes. So that's just kind of the notes they give us. It says, write a variation equation expressing S in terms of A and P. Include the value of the constant. Okay, that's part A. That's what we need to come up with. So we know that S and A are directly related. It says that. So S would be K times A if that's all we were looking at. That is a direct variation equation. But we're not only comparing that, because we also know that S is inversely related to the P. So what we're going to do is stick that over P. Because if you remember, our inverse variation problems look like this, where we had K over P, or K over whatever it was. So when we do a combination problem, we take the inverse and the direct and we combine them together. So it's usually easier to set up the direct variation first, and then you get to stick that over your inverse. This is our very general formula that they need for A. We have some constant times the advertising divided by the price will tell us the sales of their cupcakes. And luckily, if we look at this information, based on what they gave us, for their general example, notice we had an A, a P, and an S. If we know A, P, and S, we can figure out that constant of proportionality. We can figure out what our K is. And that will allow us to write a nice, more specialized equation. So I'm going to do that to figure out what my K is. I'll have 6,200 as my S equals K times A, which is 400. Oh, well, this is nice. Divided by 1. You can't see all of that. There we go. So 6,200 equals 400K divided by 400. And we find out that K is, yep, this is one of those times where I spoke too soon. K is 15.5. If you wanted to leave that as a fraction, you could. But you'd have to keep simplifying, because 62 and 4 is not simplified. So this one says include the value of the constant. So if they wanted the more specific version, we'd have to write S equals 15.5 times the advertising divided by the price. Is going to tell us cupcakes. Which is what we're going to need for B. It says determine the expected sales if the advertising budget is 600, that's our A, and the price of the cupcake is our P. We want to know how many cupcakes can we guesstimate we're going to sell if that's our advertising budget, but we also raise the price a bit. So the sale of the cupcakes will be 15.5 times the advertising budget, which is 600, all over 1.20. If you type that in, we can guesstimate that that cupcake shop is going to sell 7,750 cupcakes. This is actually what businesses have to go through when they're trying to determine production for the day, when they're trying to figure out how much they should spend on advertising versus how much they're actually getting out. When they're trying to find that sweet spot for a price of a product, this is all actually coming into play. So if you ever think about going into any type of a business sector, obviously there's math in business, but there's a lot of different kinds of math in business. It's not just business math. It's not just all taxes and dollars. It's going to be where's that sweet spot that we need to come up with? How is this all related? If I jack up my advertising, does that affect my cupcake sales? If I jack up the price of my cupcakes, how does that affect the sales? Because you'll find that you can jack the price up on some things until you hit a certain threshold. And then it's after that threshold that once you keep increasing the prices, people aren't willing to pay, even if you're doing good advertising. Are there any questions on this one? Okay, I've got one more. I wasn't sure if we'd totally get to it, but it looks like we've got time. So I made it an extra example because this one's probably about as complicated as you'll ever see. So I like to finish with it. Also note that since it's the most complicated you'll ever see, you probably won't see one like it too often. But it's good to see. It says the maximum load L for a horizontal rectangular beam varies jointly with the width of the beam, W, and the square of the thickness of the beam, T. So remember, jointly was where it was direct relation, but it had more than one variable at play. So, again, I'm going to make a lot of little notes here. It said the load of beam, that's our L, directly varies with the width of the beam. It also directly varies with the thickness of the beam, which they call T, because that was a joint variation. Joint is where you have direct variation, but with more than one item. Then it goes on to say that the load of the beam inversely with the length of the beam, which is little l. So directly with the width, directly with the thickness, but inversely with the length. And then it's going to start giving us lots of information. It says a beam is 4 inches wide 2 inches thick, 8 feet long. Will support a maximum load of 750 pounds. So all of that's going to be information that we're going to need here in just a minute. I guess it didn't matter that that was feet. First thing they're going to ask is write a variation equation expressing big L in terms of WT and little l. So even though we have a joint variation at play here, remember joint variation was direct. And I said it's always easiest to start these combination problems by looking at the direct variations. So if I'm looking at direct variations, I have the load of the beam is directly variable to K times W times T. That would be a joint variation problem if I didn't have anything else at play. Now, since I have the inverse, oh, wait a second. Oh, look what it says here. And the square of the thickness. So this should be T squared. Got to be careful about that. I almost missed that. The square of the thickness. So if it was only a joint variation problem, I'd be done. This is a combination problem where the load is also inversely related to the length of the beam. So all of that stuff that I just found for my direct or my joint variation gets put over the length of the beam. These joint or combination problems always work pretty similarly to where if you do the direct portion first, just stick it over whatever it's inversely related to, and then you move on from there. B says determine the constant of proportionality and then use it to rewrite the equation more specifically. And so that's why they give us all of this information here. Because everything listed here is all the different variables that we have in our equation except for our K. And so we're going to be able to find our K. Because it says the load is 750 when our width is 4, our thickness is 2, and our length is 8. I'm just working through the math here. So I have 16 over 8. That's going to simplify to give me 2. So to get K by itself, I would divide both sides by 2, giving me my K is 375. That is my constant of proportionality. So I need to rewrite my equation from up top so that I have the load is equal to 375 times the width times the thickness squared divided by the length. But we're not done, because there is a part C. C says determine the maximum load, which is the L, for a beam that has a width of 3 inches, a thickness of 4 inches, and a length of 12 feet long. So we're going to plug them in and figure out what that load is. So we're going to find the load. If we have 375 times the width, which is 3 inches, times the thickness, which is 4 inches squared, all over the length, which is 12. You can do as little or as much of this as you want on paper versus typing it into your calculator. Pretty much at this point when I would go to my calculator to find that the load bearing is 1,500 for this.